Alright, hi guys, we are back with fourth lesson from the chapter, lesson 1-4 on arithmetic sequences and series, right? So arithmetic, that root word there. So here's an example. We're gonna start with example 1. We're gonna look at an example of an arithmetic sequence. So I'm gonna just cover this up so we focus on that. So if this is a sequence 3, 8, 13, 18, 23, it continues on forever and ever. It's asking you to find the common difference. So when you see the word difference, you should be thinking of subtraction, right? So what is the difference between these numbers? So hopefully you're kind of seeing it. So I can notice here if I add 5, 3 plus 5 gets me to 8. In that same pattern, if I add 5, it gives me the next number in the sequence, right? So the common difference here is just 15, right? 15. Already right, is just 5. Each time we're adding 5, the common difference is 5. Okay, that part's not too hard. Okay, now we need the formula for the next term. So that we know that the next term is just going to be adding 5, right? So let's think about it. So we know that f sub 1 is 3, right? F sub 2 is not sub 2, f of 2 is 8. F of 3 is 13, right? We could write all those out. We know what those are. But what if I wanted to write f of 2 in a different way? Couldn't I also say that f of 2 is equal to f of 1 plus 5, right? I can just take my 3 and add 5 and I get my second term. Same thing for the third term. That's just going to be f of 2 plus 5. So for each term, I can just say my pattern to find the next term is to take the previous term and add 5, right? Hopefully that's not too confusing, right? So this is called a recursive definition because recursive, which I wrote down here, let's ignore this example for a second. Recursive means that you can find any term given the previous term. So as long as I know the last term, I can find the next one. I could take this same formula to find this is 1, 2, 3, 4, 5. To find the sixth term, I would just take the fifth term and add 5, right? So that's what recursive means. So I might write that down for recursive formula. So the recursive formula for this is going to be generally, I didn't give myself a lot of space here. Remember I posted no. Okay, so generally it's going to be that f of n is equal to, right? It's equal to f of 1 when n equals 1 because you have to know what the starting point is, which our case is 3. And then for every other point term, you can just take the number you're at minus 1, right? So if I was at the fifth term, I would take n minus 1 or the fourth term, and then add the common difference. And this is only true when n is greater than 1. So this is the recursive formula for finding the next term. All right, so let's figure the recursive definition for this one. So what's happening each time in the recursive formula for this? 4 to get to 7, I'm noticing that the common difference here is each term is 3 more than the last, right? So the common difference is D, okay? So if I'm gonna write it in the same way as this, right? Let's see. F sub n equals f of 1 when n equals 1, which in our case is 4, right? And then to find any other term, you just take f of n minus 1 plus d for when n is greater than 1. It's the same as this, right? Because it's the same pattern, you're just plugging in different numbers. So this is the recursive definition, but I'm also going to show you another way you could write it using, instead of the function notation, kind of this a sub n. So you could say, to find the term, like any numbered term, you would just, my notation is a sub 1 when n equals 1, and a sub n minus 1 plus d when n is greater than 1. So this is subscript notation, where this is our function notation. So these two things are the recursive definitions for an arithmetic sequence. It's going to be the same no matter what, which hopefully makes sense. If you know the last term, you can find the next one by adding the common difference to it. Okay? So that's one thing you're going to have to do. Keep moving on. What about this example here? You're given the recursive definition. So from this, I can see that the first term is 3. And to find any term, I can take the previous term and add 0.5, and I will get the next term. So we have the recursive definition, and they're asking us to find this explicit definition. So here's a definition for what explicit means. Explicit means that you're writing a formula where you can find any term without knowing the previous term, right? And this is more helpful because if you have to find the 100th term, you don't want to have to go up to the 99th and then use your explicit or your recursive formula. It would be great if you could use what you have to find the 100th term. Okay, so the explicit definition is going to depend on, let's write it here and see if this makes sense. So so to find any term, you will just take the first term, a sub 1, and add the common difference times how many terms away you are, right? So that kind of hopefully that makes a little sense. To find any number in that sequence, since it's just an addition pattern, you take the first one and add how many times you've jumped along that sequence, right? So let's put that in an example here, so maybe it makes a little bit definition, or it makes a little bit more sense. So if I'm finding the explicit formula for this, for any term, a sub n, it's going to equal the first term. What's our first term here? 3. Okay. Plus, what's our common difference? So which one of these numbers is our common difference? So if I come back and look at the recursive definition, I see that the common difference is this second term here. It's the plus d on the bottom part of the piecewise function. So when I look at my example, my common difference is 0.5. So I'm going to plug in 0.5 times n minus 1, right? So if this is the explicit definition right here, that's the answer. And I could use that to find any term. So if I was asked in the next question to find the 1,276th term, I could plug that in for n, and I would be able to get what that number is without having to add 0.5 to this 1,000 something times, right? So this is the shortcut way to do that. All right, I'm gonna move on to, so hopefully understanding the sequences makes sense, right? Because it's just an addition pattern we're talking about right now, arithmetic. And now you've learned how to write the explicit and the recursive formulas for those. So sometimes you'll be asked to find the sum of the terms, right? And of course, there's a long way to do this, which is you could find every term and add it up, right? And there's a shortcut way. So here's our next example. What is the sum of the terms in the arithmetic sequence 1, 4, 7, 10, and 13? We are lucky because this sequence is finite and only has 5 terms. So we can totally find the sum. Let's do it. Let's find the sum. So if I had to find the sum of this, let's call it the sum of the first 5 terms. So actually we can replace this with s sub 5 is going to be whatever in the world 1 plus 4 plus 7 plus 10 plus 13 is. Okay. That ends up being 35. So check, we've answered that question. The sum of that is 35, right? It's not hard when there's 5 of them. It's probably easier just to add them. But what if your finite series has like 1,000 terms? Then it's going to get a lot longer to add them, and that's why we have these formulas to figure that out. So if you need to find the sum of any finite series, meaning it has an end, right? You can take the sum of any number of terms is equal to the number of terms times a sub 1 plus a sub n. We squeeze that in there. Close the parentheses, all over 2. So you want to write this down. This is the general formula for finding the sum. You want to have that in your notebook. Now let's see if it makes sense. Let's try it here. I'm going to write it in pink using this formula. So if I had said S sub 5 equals, and I plugged in here, well, we have 5 terms in our sequence. The first term was 1. The last term was 13. All over 2. Let's see if we get 35. This ends up being 5 times 14 over 2, which ends up being 5 times 10 is 50, plus 5 times 4 is 20, 70 over 2, which, yep, ends up being 35. So they match. And let's think about why this works, right? Why this works. I'm taking my first term and adding it to my last term. Okay, so I have those two. Multiplying it by how many terms there are, and dividing it by 2, right? Because if there's a common difference here, which is what is defined as an arithmetic sequence, then this pattern lets you find the total. Okay, so then I want to introduce this. This is called sigma notation, to figure out how you can write the sum of a sequence in sigma notation. So this symbol here, if you guys haven't seen it yet, is called sigma, and it just means to add everything up. It's notation for adding everything up. So this says sigma notation, so that I equals 1, so from 1 to 9 of the summation of 2i minus 6. So the way you would say this is summation of 2i minus 6 from 1 to 9. Okay, so let's just write some of this out. A sub 1. So let's use the subscript notation. What would a sub 1 be, since we're starting at 1? That's where I got 1 from. Well, that would be 2 times 1 minus 6, right? I'm just plugging in 1 here, which ends up being 2 minus 6, which ends up being minus 4. Okay, let's do this all the way to 9. And I'm just going to write. You guys can follow along. If you want to pause it and do it all your own, and then turn it back on and see if you got them right, you can go ahead and do that. A sub 2, a sub 3 is 2 times 3 minus 6, which is 0. A sub 4 is 2 times 4 minus 6, which is 2. A sub 5 is 2 times 5 minus 6, which is 4. Go over here. Minus 6. 12 minus 6 is 6. 14 minus 6 is 8. 16 minus 6 is 10. 18 minus 6 is 12. Okay, so those are all of our terms from the first term to the 9th term. I just used this expression to figure them out. All right, so if I had to find the sum of all that, I can totally add all that up, right? So whatever, negative 4 plus negative 2 plus 0 plus 2 plus 4 plus 6 plus 8 plus 10 plus 12 is, well, that comes out to be 36. So the summation of this, the answer to this problem, which there should be a question here, is 36, right? So this is the long way to do it. How could I use this general formula to figure it out? How could I use this general formula to figure it out? Well, I could have said, I know 1 through 9 is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9 terms, right? So S sub 9 equals, let's use this formula here, 9 terms. My first term, if I could have just done this part, would have been negative 4. My last term is 12, all over 2, which comes out to 9 times 8 over 2, which comes out to 72 over 2, which is 36. So those are the 2 different ways you could have done that to find a summation. Okay? This one, a lot quicker. Okay, last example. Let me move this over, sorry. It says write the series 2 plus 9 plus 16 plus ... all the way to 79 using sigma notation. All right, so these are the steps. I have this sequence, or this series, right? It's a series because it's a finite arithmetic sequence. So there's got to be a common difference. The only thing is I don't know how many terms there are because I don't know how many are in between 16 and 79. I could figure it out by finding the common difference, right? And then counting, but there's a faster way to do it. So let's start with finding the number of terms. All right, so how are we going to find the number of terms? So a sub 1 we know is 2, and a sub n we know is 79. We just don't know what that n is. But if I know a sub 1 and a sub n, I know I can come back, go back to our notes. I know that I can use this explicit formula to help me find the number of terms, right? I know a sub n and I know a sub 1, and I can figure out the difference then that will help me solve for n, the number of terms. So I'm going to write the explicit formula over here real quick. So I know a sub n equals a sub 1 plus d times n minus 1. Okay, now let's plug in what we know. A sub n is 79. A sub 1 is 2. Common difference, what's happening here? Every time is plus 7. Hopefully you guys can see that. If it was not plus 7, it wouldn't be an arithmetic sequence, okay? So now I'm going to plug in 7 for d, and n is the thing I don't know. So now you get to use your algebra to solve this, right? I'm going to try to squeeze it in here. Let's go a little bit smaller. So we end up with 79 equals 2 plus, let's distribute that 7 in, 7n, and then 7 times negative 1 is negative 7. So you guys didn't forget that stuff. Now let's combine like terms. So I can put 79, 2, and negative 7 together. Okay, let's just do the right side first. So I end up with 79 equals 2 minus 7 is minus 5, and we still have plus 7n. Now I can move that 5 over, and I end up with 79 plus 5 is 84 equals 7n. And now I can divide by 7. And what is 84 divided by 7? I feel like I just made a mistake. You guys get to see my mistakes on the live on YouTube. 84 divided by 7. Oh no, that's right. Okay, so 84 divided by 7, that cancels out, and 12 equals n. So I know that there are 12 terms here. Here's the first one, and here's the 12th term. I just didn't know my division facts. I thought I had a decimal there for a second. Okay, so we know that there are 12 terms. Now I can write the explicit formula because I can take this thing and plug in everything I know. A sub n equals, a sub 1 is 2, plus, we already figured out d is 7, and then n minus 1. Right? So we know all of those things. Which then we can actually plug in we want to simplify it a little bit more. Since this is finite, we know there's only 12 terms. We just figured that out. So it ends up becoming that a sub n equals 2 plus 7 times 11. Let's just check if this is right. So a sub n, well this is, now we're figuring, since we plugged in 12 here, this is a sub 12, right? So a sub 12 ends up being 2 plus 77 is 79, so that's right. But here's our initial explicit formula. Okay, and you could simplify that because you could say a sub n equals 2 plus 7n minus 7, right? If I distribute that 7 in, which means a sub n equals 2 minus 7 is negative 5, so 7n minus 5. So if you had a multiple choice test and it said, what's the explicit formula? You might see it like that, or you might see it where they just went ahead and multiplied the 7 and distributed that in, that common difference. So either of those are correct, okay? Now, the question asks us to put it in sigma notation, so we had to do all this so we could put it in sigma notation, right? So we know we have to figure out I, right? What's the first term? We know that we're starting with the first term. Okay? So I is going to be 1. N, the n term, we're only going up to the 12th term. So let's go ahead and write our sigma notation. Let's use this other one we had as an example here. So the last example, I was 1, we went to the 9th term, and then you just write the explicit formula here. So, same thing. We're starting off with the first term, so I equals 1. We're going to the 12th term, and then we just write our explicit formula here, except we have to replace the n with an I, because that's what sigma notation asks us to do. So I can just write 7i minus 5, which I just got from here. Just change the n to an I. You could also use that one. This one's more simplified though, and more likely to be what you see. Okay, now that we have the sigma notation, we did all this stuff, we can actually find the sum of the series. Let's use that general formula, S sub n equals n a sub 1 plus a sub n all over 2. So we have 12 terms, plugging in 12 for n. A sub 1 is 2. A sub n is 79, getting that from up here, all over 2. Now we just have to do some math here. So S sub 12, some arithmetic, ends up being, when you work all this out, 12 times 81 over 2. You can cancel that, and you end up with 486 as your final answer. Okay, and you can work that out on your own to figure out 46. All right, so hopefully you understand those arithmetic sequences a little bit. Try the practice problems and connect if you have any questions, okay? Bye.